Today we're going to talk about, we're going to continue talking about section 3D in your textbook, which is on invertibility and isomorphic vector spaces. So last lecture, we began talking about these things, and we said that an invertible linear map is one for which there exists another map going the other way that undoes it, right? So you call T invertible if you can find a linear map S such that ST is the identity and TS is the identity. And since, if such a map exists, you call it an inverse, and we showed that inverses are unique. So if a map is invertible, then it will have a unique inverse, which we denote by this T inverse. And then, well, that seems like something that might be maybe hard to check, right? If I just hand you a map, how do you figure out, is there a map going the other way that undoes it? There's a very clean criterion for when a linear map is invertible. It happens if and only if the map is injective and surjective. Okay, so we'll begin today by proving this theorem. Okay, so let me just restate it. A linear map is invertible if and only if it is bijective, which means it's both injective and surjective. And this, again, does not use, I'm not assuming anything is finite dimensional here. So this will work totally in general for any vector spaces you want. Okay, so this is an if and only if. Let's prove the first direction. So suppose that T is a linear transformation, a linear map from V to W that is invertible. So I'm trying to show that it's both injective and surjective. Okay, so first we show it's injective. How do you show that a map is injective? Well, you suppose that you got two of the same output and you try to prove that it came from the same input, right? So suppose that you have two vectors, u and v, such that tu equals tv. Okay, I want to show that u equals v. But right now I've got tu and tv. I want to somehow go back to w. Sorry, tu and tv, these are vectors in w. I somehow want to go back to v. Well, I'm assuming that t is invertible, which means it has an inverse, right? So now you just apply the inverse map. T inverse, which I'm assuming exists by hypothesis. Right? So since tu equals tv, that means that if you apply T inverse to these, you get the same thing. But by the definition of the inverse, this is u, this is v. So I've shown that T is injective. Okay, what about surjective? Next, show that T is surjective. How do I prove the map is surjective? I need to prove that any vector in W is in the range of T. Right? So let W be in W. I need to find a vector in V that maps over to it, right? I need to find something to plug in here to give me W. But again, I'm assuming that T is invertible. What I have is the inverse map, which means that if I plug in here T inverse W, right? So then T inverse W, this is a vector in V. And if you apply T to it, you get W. So this means that W is in the range of T. So every vector is in the range. That means that T is surjective. Right, so that proves that direction. Every invertible map has to be bijective. Sorry. Every invertible map has to be both injective and surjective. Okay, let me just make a remark that actually all the stuff that we did here, this holds for any function. Right? Here I am not using anything about the linearity of T. This is just true totally in general. If you ever have an invertible map between two spaces, it's got to be bijective no matter what. Okay, but to show that bijective implies invertible, we're going to use the linearity of T. So suppose that T is bijective. What I need to do is I need to construct an inverse. So we want to construct a map S going from W to V such that ST equals TS equals identity. Oh, sorry, ST is the identity on V and TS is the identity on W, but such that S is the inverse. I need to actually construct an inverse. So in order to find a map from W to V, I need to say what it does to every W and W. So for each W and W, define SW. This thing is going to be a vector in V to be the unique vector in V such that when you apply T to this vector, you get W. Okay, so I'm trying to define a function from W to V. I've said you start with a W. Which vector in V does S spit out? It spits out the unique vector that maps to W. Okay, but why is there a unique vector? Why does this exist? Well, the point is that I'm assuming that T is bijective, right? So since T is surjective, it means that W is in the range. It means that I can find a vector to plug in here. But since T is injective, there can only be one vector mapping over to W, which means that there's only one possible vector that I can plug in here, and that's how I'm going to define S, right? So SW exists since T is surjective, and it's unique since T is injective. Okay. So now that I've now successfully defined a function, right? So this defines a function. However, I still need to show that it's a linear map and that it's the inverse. Okay, so why is S linear? Maybe I should say claim S is linear. Okay, so how do you show that it's linear? You need to show that it respects additivity and it respects scalar multiplication. So let's take two vectors in W. Well, let's consider the following. Let's say I apply T to the vector SW1 plus SW2. Okay, well, T is a linear map. So since T is a linear map, I can definitely split this up over the sum. This is by the linearity of T. And now by the definition of S, this is W1 plus W2. So this is by the definition of S. But what does this say? This says that the vector that maps over to W1 plus W2 is exactly the vector SW1 plus SW2. Right? Which means that SW1 plus W2, this was supposed to be the unique vector mapping to W1 plus W2. This says that it's exactly the vector SW1 plus SW2, because that's a vector that has that property, which shows that S respects addition. Okay, and then you do a similar thing. Proof for scale multiplication is similar. Right? So what do I mean by that? You need to show that S of lambda W equals lambda S of W. So you just prove that this vector maps over to lambda w. And since that maps to lambda w, that is by definition S of lambda w. Okay, so S is linear. Okay, and then finally, we need to show that S is the inverse. In other words, i.e., if you do ST, you get the identity on V, and TS, you get the identity on W. Right, so let's do the second one first. For any W and W, what is TS of W? Well, by the definition of SW, this was exactly supposed to be the unique vector that mapped over to W under T. So this means that TS is the identity on, this is just by the definition of S. Okay, now, but we need to now consider the other way. Why is it that ST is the identity on V? Okay, so there's a little trick here. Actually, I was told when you're teaching math, you shouldn't ever call something a trick because it makes it seem mysterious. I should call this a technique. Right? So once you learn the technique, you can use it again. Although it's really just a little trick. So let's let V be in V. Then, okay, so I'm interested in something like ST of V. But I sort of don't know what T does to V, right? Because T here could be any linear map. So the technique here is to apply T again. Okay, why is that? Because function composition is associative. And so this is the same thing as doing TS of T of V. And I just showed that TS was the identity on W, so this is just T of V. Well, why is this good? Because now we have T of this thing, T of this thing equals T of this thing. And also, in this part of the proof, we're assuming that T is injective. So if the T of this thing equals this thing, it means that these two things are equal. So since T is injective, by hypothesis, this means that S of T of V equals V. This is true for all V and V, which means that ST is the identity on V. So I've shown that if you assume that T is bijective, you can define this function, this S, and that's a linear map, which is an inverse to T, which means that altogether, so T is invertible with inverse S, which is what I wanted to show. Okay, so this is a very powerful theorem because for one thing, this theorem tells you how to construct the inverse to T if you know it's bijective. But if you don't care about what the inverse is, you just want to show that it's invertible, you only need to check these two things. Just, is it injective? Is it surjective? And that is easier than trying to cook up an inverse, which is like trying to define an entire function. Okay. So now we begin talking about isomorphic vector spaces. Okay, and just some etymological discussion, right? Iso, I think this is Greek, right? This means shape, sorry, same. Like an isosceles triangle has two sides to the same length, right? An isotonic solution is at equilibrium or something. It's been a long time since I took chemistry. And morphic, this is shape. Okay, so isomorphic vector spaces should be some notion of two vector spaces having some kind of sameness. Well, why would this concept be useful? Because sometimes we'll have two vector spaces that are basically the same vector space, but they're not equal. So, and this first example that I'm going to talk about is one that I know comes up even in 308 pretty often, which is let V be the xy plane in R3, right? So what is that? That's the set of all vectors x comma y comma 0, where x and y are any real numbers. Okay, and you could also express this as the span, right, of these two vectors. It's another perfectly good way to describe it. I guess you could also describe it as the null space of something. But it is very sorely tempting to say that this is equal to R2. Okay, but it's not. These two things are not, these two vector spaces are not equal because R2 is defined to be the set of all ordered pairs of real numbers. And the elements of this vector space V are all triples of numbers where the third coordinate is 0. Right? So these vector spaces look and behave very similarly, but they're not equal because the elements aren't the same. It turns out that the notion that you want to talk about to say that two vector spaces are the same, a more useful notion maybe is that these are isomorphic vector spaces. They're the same in some way. Isomorphic, not equal. Okay, because equal means like actually the same, containing exactly the same elements. Okay, but so why do these behave the same way? Like, how can we see? Well, one way to see this is that there's a linear map. T from V to R2, where it just sends a vector x, y, 0 to the vector x, y. Right, and this map is linear. That means it preserves addition, preserves scale multiplication, and it's injective and it's surjective. Right, so this is it is bijective. So this map T is really, right, and like in your mind when you're learning 308 and learning about the xy plane in R3 and the vector space R2, you're using this map to go in between these two vector spaces, right? You're regarding the vector, the reason why you sort of think these are the same is because you regard the vector x, y, 0, the thing sitting on the xy plane, you're like identifying it in your mind as the point x, y, in R2. You're really using this bijective map. So the idea here is that when we're talking about two vector spaces acting the same way, even if they're not equal, really the notion we're talking about is the existence of a bijective linear map between them. Or we just saw that a bijective linear map, that's the same thing as an invertible linear map. So you could also say it's invertible. Okay, so somehow, really, this notion of an invertible linear map between two vector spaces is saying that those two vector spaces behave essentially the same way, even if they're different. Okay, so we give these things a special name. An isomorphism is an invertible linear map. If there exists an isomorphism from a vector space V to a vector space W, then we say that V and W are isomorphic. Isomorphic. Okay, note that this is sort of a redundant definition. I've just redefined, I've just given a new word for invertible linear map, right? A map is an isomorphism if and only if it's invertible. So it seems like this is a redundant word. You just use the term isomorphism when you really want to stress, when the important part of what you're talking about is the fact that the vector spaces are basically the same. You would use the word invertible when you really want to stress that there's a map going the other way, when that's like the important thing that you're concerned about, right? And then this word isomorphic, I guess that's a new word because we don't have a word for that. But really the way that you should think about this is isomorphic vector spaces are basically the same, essentially the same. Okay, then one kind of common thing in mathematics is wanting to classify things. Right, so for example, you might want to, I don't know, classify all right triangle with integer side lengths or something, right? Or you might want to classify all surfaces that have one hole in them, right? Like this surface, the surface of the donut, this is called the torus, this has one hole. You might want to say, okay, well, what other surfaces have one hole in them, right? One thing you could ask is, well, what are all of the vector spaces? Let's actually just ask a simpler question. What are all of the vector spaces of dimension 2? Well, the problem with that question is that there's tons of them, right? I mean, here are 2 vector spaces of dimension 2, right? This R2 is 1, B is 1. But then, of course, you can take any plane to the origin in R3 and write down an invertible linear map to R2. You can take any plane to the origin in R4. You could take all the linear polynomials. So if you're trying to classify every vector space of dimension 2, there are just too many to think about, right? There's something you never ever thought about, never ever will think about. But instead of trying to classify all vector spaces, you could try to classify all vector spaces up to isomorphism, right? So in that case, these 2 vector spaces, I'll just consider them the same because they're both isomorphic. In a similar way, instead of classifying all surfaces, right? So, right, like this donut is bigger than this donut. These are different donuts. But if I'm only concerned about the number of holes in the surface, then these are basically the same, right? Because I can just shrink one to the other. So these are isomorphic in some topological sense. So the motivating question is, what are all the vector spaces of dimension 2, say over R? Again, this question is too hard to answer, but what about up to isomorphism? Right? Maybe there's only a couple up to isomorphism, right? Because these 2 are the same. So I haven't added anything. I'm still only in the realm of things that are isomorphic to R2. Are there any ones that aren't isomorphic to R2? And a very nice theorem is that the only 2-dimensional vector space over R up to isomorphism is R2. Okay, so every 2-dimensional vector space over R is basically R2, even though it's not necessarily R2. And this is true in every finite dimension. So let V and W be finite dimensional vector spaces over our field F. Then V and W are isomorphic. If and only if they have the same dimension. Okay, so this says that in the finite dimensional case anyway, just knowing the dimension of a vector space tells you everything about how the vector space behaves. If I tell you that I have a 12-dimensional vector space, it's basically F12. Right? All the things that you, like whatever you prove about F12 in the abstract will be true about this 12-dimensional vector space. It's a very nice, useful result. So let's prove it. So let's suppose that V and W are isomorphic. Right, so suppose V and W are finite dimensional and V and W are isomorphic. Well, what does that mean? That means there exists an isomorphism. Let's call it T from V to W. Okay, well, T is an isomorphism. That just means that it's an invertible linear map. So T is bijective. Right? As I said, the notion of an isomorphism is just the same thing as the notion of an invertible linear map, and we just proved that invertible linear maps is the same thing as bijective linear maps. Since T is bijective, since it's injective, it's the null space of T is equal to just the zero vector, and the range of T is everything. Okay, I'm trying to show that V and W have the same dimension. A really nice theorem to use if you're interested in the dimension of some vector spaces is the rank nullity theorem, or by the fundamental theorem of linear maps, but I'm going to call it rank nullity. So by rank nullity, the dimension of the domain is equal to the dimension of the null space plus the dimension of the range. But the dimension of the null space is 0. The dimension of the range is the dimension of W. So this proves this direction. Okay. What about the converse? So conversely, suppose that you have two vector spaces of the same finite dimension over F. Right, and let's say that they both have dimension D, right, just so we can give it a name. Okay, so I need to show that there's an isomorphism from V to W. Okay, well, the way that I'm going to do this is I'm going to use our theorem that says that I can send a basis for the domain anywhere I want. Okay, so let's choose bases, right? So since these are both dimension D, let's choose bases. And these bases will have length D. Okay, so of course I mean for V and W respectively. Okay, so by a previous theorem, which I'll give you the precise citation in the notes, by previous theorem, there exists a unique linear map T from V to W such that T of Vi equals Wi for all I between 1 and D. Right? We have a theorem that says there is a unique linear map that sends a basis to any vectors that you want. Okay, so this T is going to be my isomorphism, but we still need to show that T is injective and surjective. Once we know it's bijective, then it's invertible, then it's an isomorphism. So why is it injective and surjective? Well, since W is a basis, since the Wi's are a basis, is the basis of W, this means that for every vector little w in W, there exist constants such that W is a linear combination of these basis vectors. Right? This is what it means to say that the W's are a basis of W. I'm trying to show that T is surjective at the moment. I'm trying to show that I can find a vector that maps over 2W, right? Which vector do I take? Well, I'll just take the same linear combination except of the V's, right? So then T of C1, V1 up through CD, VD. I apply linearity of T, right, to break it up over the sum and pull out the scalars. And then the definition of this linear map sends all the VI's to the WI's. right? So this shows that every vector is in the range. Ergo, T is surjective. I need to show that T is injective. In other words, I need to show that its null space is just 0. So let's suppose that TV equals 0. Okay, well, I need to figure out something about what T is doing to V. What I know is what T does to the VIs, so I should write V as a linear combination of the VIs. Right, so I'm supposing I have V in the null space, and I'm going to write C1 this V as a linear combination of VIs, since the VIs form a basis. Well, this means that T of this, which by the same computation before, right? This is T of V, by the same computation as before, just done one more time. This is equal to 0, since T of V is 0. But the W's were a basis, which means that they are linearly independent, which means that the only linear combination of the W's which equals 0 is a trivial one. So since the W's were a basis, they're linearly independent, and since they're linearly independent, this means that the C's were actually all 0, which means that V, this vector V, is a 0 vector, which means that the null space of T is trivial, which means that T is injective, which means that T is bijective, which means that T is an isomorphism. Okay, so this nice result is that finite dimensional vector spaces are characterized just by their dimension. Every finite dimensional vector space of the same dimension is isomorphic. Okay, so the concept of isomorphic vector spaces captures vector spaces that are the same. So isomorphic, this somehow means the same. And let me just bring your attention to the fact that we saw something like the fact that linear maps, if you take the set of all linear maps V to W, this is the same as the set of n by m matrices. Right? Every linear map gave a matrix, every matrix gave a linear map. In other words, these two vector spaces, right, because the set of linear maps and the set of matrices were actually vector spaces, they had addition and multiplication, there should be some isomorphism between them, which makes precise what we mean when we say that, oh, well, linear maps are the same thing as matrices. Okay, so the linear maps, so I said n by m. I should be careful here. I think before I actually said m by n, and it was between vector spaces of dimension m and n, except in the order that I just, from fn to fm, I can make the substitution because every vector space of dimension n is basically the same thing as fn, right? It's isomorphic. So this is really the precise idea that we want to capture. So that's the result of the next proposition. It says something like there's an isomorphism between linear maps from a vector space of dimension n to vector space of dimension m and matrices. But the statement is extremely precise. Okay, so suppose V1 up through Vn is a basis of V, and W1 up through Wm is a basis of W. Okay, then for each linear map, so that's a T from V to W, I'm going to let MT be the M by N matrix of T with respect to this fixed basis, with respect to these bases. And so we talked about how if you have a linear map and two bases for the vector spaces, you can write down a matrix. Again, the columns of this matrix are given by the image of each V written in terms of the W's. Okay, but this takes a linear map and spits out a matrix. So I can think of this as a function. So then the function M from the set of linear maps to Fmn, right, where you plug in a linear map and it spits out a matrix. So the one that sends T to MT, this is an isomorphism. Okay, so I should point out that we proved already that M is linear. Can I find out where we did that? Somewhere. It's probably before here. Okay. I said we proved. What I really meant was I told you to prove. This says that M of S plus D is M of S plus M of T. M of lambda T is lambda times M of T. In other words, this says that M is a linear map. So we checked M as linear. Okay, this statement is true because I've certainly checked it in my life, and I told you to check it, which means that you've checked it. So now we've all checked that M is linear. Okay, what we need to do is we need to prove that M is surjective and injective. Okay, so first we prove injectivity. So let's suppose that I have something in the null space. That means I have a map that maps over to the zero matrix, right? T is a linear map such that M of T is the zero matrix. Okay, well, what does that mean? The definition of the matrix of a linear transformation was that the columns should capture T of each Vi. But the columns of M are all the zero vectors, which means that T of each Vk equals 0 for all k. Since the columns of M, those are the T of Vs, and the columns of M are all the zero vectors, it means that all the T of Vks are 0. Okay, but now you have a linear map that's 0 on every basis vector, which means that it's 0 on every linear combination of every basis vector. So this means that T is the 0 map, i.e. T equals 0. So this shows that M is injective because the only thing in the null space is 0. Okay, what about, what about surjectivity? So let's suppose I have a matrix in the codomain of this function. What do I need to do? I need to find a linear map whose matrix is this fixed matrix A. Right, so I need to find a linear map such that the matrix of the linear map is A. Okay, but let's just define it like this. Define T as a map from V to W by T of Vk equals basically what's going to end up being the kth column of A. Okay, so what am I doing? I'm trying to find a matrix. I'm trying to find a linear map that gives me the matrix A. But the way that you get from a linear map to a matrix is by seeing where T of V goes and writing it in terms of the W's. That gives you the column of the matrix. So that's what I'm trying to do here. T of this V is going to be a linear combination of the W's given by the kth column of A. Okay, why am I allowed to define a map like this? Well, we have a theorem that says you can send a basis anywhere you want. These V's are a basis of V, so I can send it anywhere I want. I'm going to send it in particular to this particular linear combination of the W's coming from the kth column of A. Okay, but then, by definition, the matrix of T with respect to these two bases is exactly A. So this means that M is surjective, which means that I'm done. Okay, so I mean, this last part was like a little bit technical, I guess, but if you understand the last part of this proof, I think it's a good sign that you understand how to go from a linear map to a matrix, and also how to work with this notation of matrices. So I don't think it's like an easy thing to do. So you need to think about it, something that you need to think about, but you can do it. Okay. So now we know that these two vector spaces are basically the same, which, by the way, means that they must have the same dimension. Right? So these two vector spaces are the same. And we already saw that, or we talked about why the set of m by n matrices has dimension m times n, which means that this vector space also has dimension m times n. So corollary, the dimension of the set of linear maps from V to W equals the dimension of V times the dimension of W. Okay. I haven't stated that I want them both to be finite dimensional, but I do. Right? Otherwise, the dimensions don't make sense. Okay. Now we have one last definition in this section. And it's again kind of a redundant definition, but oftentimes when there's a redundant definition, it means that the particular thing you're defining still has some use, right? There's some reason why you want to define it more than once. So what do I mean? A linear map from a vector space V to itself is called an operator. Okay, and we use the notation LV for L from V to V for the set of all operators. Okay, so I'm just defining a new word. In the case of the domain and the codomain are the same. I call that an operator on V. And these have a special name because studying operators is often a very useful thing. There's more structures on the set of operators, for example, right? So we said that you can, for example, compose two linear transformations if the domain of one matches the codomain of the other, right? But we said that in general, if S is from U to V and T is from V to W, then ST is from U to W. These three things all live in different vector spaces. But if you compose an operator with another operator, you get an operator, right? If all those vector spaces are the same, then you can compose maps and you keep on getting things that are operators. So this means that the set of operators, for example, has a multiplication on it. So studying the operators is a useful common thing in mathematics. Okay. So the last result in this section has something to do with invertibility of operators. So what's the first thing we proved today? The first thing we proved today is that linear transformations are invertible if and only if they're bijective. Okay, but for an operator, it seems like maybe you don't need to check both things. So for question, for an operator, does injective imply bijective? Okay, why does this seem like not a crazy question? Because, for example, if I tell you that I have a map, let's be very concrete here, from the set 1, 2, 3, 4 to the set 1, 2, 3, 4, and I tell you that it's injective. In other words, every element goes to a distinct element. If you have a function like this, then f being injective implies that f is bijective. Right? There's no way to be injective without being surjective from this set to itself. Right? Of course, you can have an injective map to a different set. Right here, f being injective does not imply that f is bijective. But this is what wouldn't count as like an, maybe I'll call this G. In this setting, the domain and the codomain are different. So they could be anything. So injectivity doesn't say anything about surjectivity. But in the case when you go from one space to itself, at least in set theory, seems like injective is actually the same thing as bijective. Actually, if I told you that f were surjective, if I said, oh, well, this function hits everything in 1, 2, 3, 4, well, then everything must have gone, 1, 2, 3, and 4 must have all gone somewhere different under f. So this is also true. So can we say something stronger about operators because we know the domain and the codomain are the same? Well, even in Math 300, this thing that I wrote down is still not exactly true. I mean, okay, everything I've written down so far is true. Right? There was a question mark over this. But we know that you can have a map from the integers to the integers that sends, say, x to 2x. But this map is injective, but not surjective. It only hits the evens, right? But it always sends different numbers to different numbers. Okay, the issue with this is that this is an infinite set. So while it's true that if you have a function from a finite set to itself, injectivity implies bijectivity and surjectivity implies bijectivity, is not true for infinite sets. Which in our setting of linear algebra should mean that there's a difference between the finite dimensional and infinite dimensional cases. So if we're going to find some bad behavior, it should be for infinite dimensional things. Okay, so if you consider the left shift operator from f infinity to f infinity, right? Again, the one that sends every vector to a shift of itself, shifting to the left. This thing is not injective because it sends 1, 0, 0, 0, 0, 0 to 0. Right? So the null space is not trivial. However, it does hit every vector. If you want to hit any vector, you just shift it to the right first, and that vector, you plug it into L, will give you the vector you want. So this map is surjective, but not injective. Okay, similarly, the right shift operator, the one that just adds a 0 to the beginning, this thing is definitely not surjective because you can never get a non-zero first coordinate in the image. But the only thing it sends to 0 is the 0 vector, so it is injective. Okay, and then I have one other example in the notes, which you should read. The operator that's given by multiplication by z. It's not anything too crazy, so I don't mind not explaining it. But since in Math 300, this kind of thing was true for finite sets, but not infinite sets, it suggests that maybe the result that we want is the result about finite dimensional spaces that won't necessarily hold for infinite dimensional spaces. And this is exactly true. Okay, so suppose that V is now a finite dimensional space. And T is an operator on V. Then the following are equivalent. Right, so that's what this means. I will use it henceforth in this class. I reserve the right to abbreviate it. So T is invertible is the same thing as T is injective is the same thing as T is surjective. Okay, and also we have a result that says invertible is the same thing as bijective. Okay, so injective and surjective and bijective are all equivalent for a finite dimensional space, an operator in a finite dimensional space. Okay, so we already proved, okay, so sorry. We proved that invertible implies bijective. So we already saw, that's by the first result today, that 1 implies both 2 and 3. Okay, so it suffices to show that 2 and 3 imply each other. Right? Because if 2 and 3 imply each other, sorry, we showed that 1 is if and only if 2 and 3. So since we show that 1 is if and only if 2 and 3, certainly if 2 is equivalent to 3, then if you have 2, you also have 3, which means that you have 2 and 3, which means you have 1. So 2 will imply 1. Right? So it's enough to show that 2 and 3 are equivalent in this case. So let's show that. Let's show that injectivity and surjectivity are equivalent for an operator on a finite dimensional space. So let's show that 2 implies 3. Okay, so suppose that T is injective. Then this is equivalent to the null space of T being trivial, which means that by the rank nullity theorem, the dimension of the domain is equal to the dimension of the null space of T plus the dimension of the range of T, which means that the dimension of the range of T is equal to the dimension of V minus the dimension of the null space, which the dimension of the null space is 0. So the range of T is everything, which means that T is surjective. Okay, and the other way goes essentially exactly the same. Similarly, if T is surjective, we again use the rank nullity theorem, except we just solve for the other one. So the dimension of the null space of T equal to the dimension of V minus the dimension of the range. But this is 0, which means that the null space is trivial, which means that T is injective. Okay, so by the rank nullity theorem, we'll have injectivity is equivalent to surjectivity for an operator. Okay, this theorem seems kind of simple, actually. I mean, the proof is pretty short. It's like a very, it doesn't seem like it's saying very much. But there's a very cool example in your textbook. An example that, I hadn't thought about an application like this until I saw it. What's the example? Here's the question. Show that for each polynomial Q, there exists a polynomial P such that if you take this polynomial, x squared plus 5x plus 7, and you multiply it by P, and you take the second derivative, you get Q. Okay, this, I guess you could theoretically do just after you take Calc 1, right? So you write down Q as a generic polynomial with a bunch of variables. Then you integrate twice, including some constants of integration that you have some control over. Then you try to adjust the constants of integration so that you can divide by x squared plus 5x plus 7. And then you divide and you try to write down p in terms of the coefficients of q plus the two constants of integration plus the division. Okay, but this seems very painful. I certainly don't want to do it. But it turns out that you can use the previous proposition to figure out that this statement is true in the abstract without ever having to write down a variable coefficient to solve for. Okay, so painful, question mark. Let's just use the previous proposition. Okay, but big problem to start with. The set of all polynomials is infinite dimensional. This theorem only applies to finite dimensional vector spaces. Okay, but each particular polynomial q has finite degree. Say m, and then you can think of q as living in this smaller finite dimensional vector space. Okay, so I just start with an arbitrary polynomial q, but I can think of it in a finite dimensional vector space. And now if I define an operator in this finite dimensional vector space, the previous result would apply. Okay, so let's define an operator T on this finite dimensional vector space. Whoops. What does it do? It sends a polynomial P to, you first multiply it by x squared plus 5x plus 7, then you differentiate twice. Okay, let me just note that here you've multiplied P by a quadratic, so you've increased its degree by 2, and then you differentiate it twice, so you've decreased the degree by 2. So if you start with a polynomial of degree no more than m, the result is a polynomial of degree no more than m. So this is in fact an operator on this finite dimensional vector space. This is an operator on a finite dimensional vector space. What am I trying to show? I'm trying to show that this operator is surjective. I'm trying to show that you can get any q you want out of it because that's what the problem is asking me to show. But it's enough to know that it's injective because on a finite dimensional vector space, injectivity of an operator is equivalent to surjectivity. So let's suppose that T of P is 0. Okay, well, if T of P is 0, it means that this thing is 0. So if a second derivative gives you 0, it means that the thing you took the second derivative of was linear. Right? That means that this thing is a linear polynomial. Those are the only polynomials that have 0 second derivative. Okay, but now we have a degree 2 thing times something equals a degree 1 thing. But polynomials never go down in degree unless they get multiplied by the 0 polynomial. So this means that P is a 0 polynomial, which means that T is injective. Okay, but if T is injective, then by the previous proposition, this implies that T is surjective, which means that I can get any vector, any polynomial q that I want out of this operator. And since q is arbitrary, it means I can get any polynomial at all as the second derivative of x squared plus 5x plus 7 times something, which is a very non-obvious fact, I think. All right, so just a note about what we're doing next. So the next section, as you probably predicted, is 3e, but in 3e, we will only cover half of it. So next time. So in 3e, there is products and there's quotients. So we won't talk about quotients. We'll only talk about products. And then we'll also begin to talk about 3f, which is on duality. All right. That is that.